speaker today is Jake Thomas. He's from the MathSys program at Warwick, and he's going to be giving a talk named Differentiating Random and Deterministic Uncertainty in Reinforcement Learning. Yeah, so Jake.
Okay, thank you. My name's Jake, part of Math. In the first year of the PhD, and broadly, my research could be described as applying possibility theory to reinforcement learning. But today I'm going to talk about why that is a sensible thing to do more than what I've actually been doing, because I will have not been going for too long. So I'll first tell you what reinforcement learning is in case anyone doesn't know, and then tell you what deterministic and random uncertainty are, and then talk about ways of modeling deterministic uncertainty and how we can do that with possibility theory, and then how that will how possibility theory can then be applied back to reinforcement learning. So what is reinforcement learning? Fundamentally, it's an agent interacting with their environment and learning from that experience, what we might call in the real world trial and error. To me, this is the most natural way of learning. For example, if I asked you to learn to juggle, say, you would like make a number of attempts at it, and the effect would be fed back to you, and you would receive rewards based on whether you actually managed to juggle or not, and you would vary your actions until you found a good way to do it. And more formally, agent at a state, which selects an action according to some policy. This will have some effect on the environment, and the effect is fed back to the agent through an interpreter in terms of a new state and the reward. And then based on that, the agent will update their beliefs about the environment and their policy about what actions to take, then take another action, and so on. So a very common example would be a computer controlling a driverless car. Can take actions in terms of steering input, acceleration, braking, and then it gets updated states from cameras, GPS, and would get rewards for example, arriving on time, fuel efficiency, comfort, and not crashing, staying on the road. And clearly, there's a lot of potential locations for uncertainty in that system, as there are in most reinforcement learning problems. Actions may not have the effect on the environment that you expect. E.g., if you're braking in the rain, then you might take a lot longer to come to a stop than in the dry. Rewards are uncertain because, well, maybe one example would be perceived comfort of the passengers, because that'll be dependent on human factors, and even the state will potentially be uncertain because the GPS measurement could be wrong. Yeah. So the point is that uncertainty plays an important role in reinforcement learning problems, which means we need to be able to accurately describe it. So types of uncertainty. So there's two main ways you can split up uncertainty into random or statistical uncertainty, and that's uncertainty induced by some truly random mechanism. So for example, rolling a dice. Between successive experiments, the value will change and you can do nothing to predict it. You can only learn the distribution. And systemic or deterministic uncertainty is uncertainty we have about fixed quantities. So if all three of those doors were closed and there's a goat behind one of them, you are uncertain about where the goat is, but where the goat is not inherently random. The goat is behind one of the specific doors. There's no superposition goat hiding somewhere. So, and then going back to the example of rolling the dice, there is the random uncertainty, which is the value you get on any particular roll, but there would also be deterministic uncertainty, because, for example, this very dodgy dice here, you would not know what value, so the probability of getting 5, say, you don't know that at the start, and it's something that is fixed, but is uncertain until you've played enough games and you gain enough information to learn what it is. And that links into this. So one of the key ways to differentiate between the two types of uncertainty is that deterministic uncertainty can be resolved by more information, whereas random uncertainty can't be. So another quick example is the Galton board, which is on the right. So if you've not seen this before, there's balls dropped from the top and they bounce off a number of pegs on the way down and then fall into a number of different slots. And the final position of any particular ball is uncertain and random, but the expected final distribution is fixed. It should be approximately normal with some mean invariance. But if you've never seen this before and don't have enough statistical knowledge to figure it out, the final distribution would be an example of deterministic uncertainty, which would be resolved as you gained more information as the balls drop. So the random uncertainty of where any particular ball will end up can't be resolved, but the deterministic uncertainty of the final distribution can be resolved via more information. And modeling deterministic uncertainty is essentially a problem of modeling information rather than probabilities. So modeling deterministic uncertainty. So we'll consider a specific example here of some samples of a random variable y drawn from a probability distribution py theta naught, which is fixed, which comes from a family of parametric distributions. So obviously, the value of theta naught is an example of deterministic uncertainty. You don't know it, but it's fixed. So the frequentist approach for, I'm not going to go into too much detail about this because I'm sure you all know, or at least passingly familiar with it. But I want to highlight the strengths and weaknesses of both approaches. So the frequentist approach represents theta naught accurately as a fixed value, and uncertainty is described by confidence intervals, which is good because theta naught's being represented faithfully and everything's relatively easy to compute. But the bad thing is that we don't have a full characterization of the uncertainty. We don't know how the uncertainty is distributed. Whereas with the Bayesian approach, the uncertainty about theta naught is modeled by a random variable x, and we can represent prior information with the probability distribution px, and then through Bayes' formula find the posterior distribution, which is good because it provides a full characterization of the posterior uncertainty with quite a natural interpretation. But it's not great because it can be computationally demanding because of the integral on the denominator. It's not faithfully representing theta naught as a fixed value. But the main issue from a theoretical standpoint is that probability distributions can be too restrictive when you're trying to model information. So by that I mean the demands placed on the behavior of the distribution because of the definition of probability measure means it can't always reflect information properly. So for example, priors. You quite often want to define an uninformative prior because you have no information, like you would at the start of a RL problem. But in a lot of circumstances, such as when you have an infinite space, these are not particularly easy things to define and can be impossible sometimes. So, and the underlying issue that's causing that is additivity, which is required by the definition of probability measure. But additivity doesn't necessarily exist when you're talking about information. For example, if I said theta naught, oh wait, maybe I should be on the next slide by now. Yeah, if I said theta naught is either -1 or in zero infinity, then it doesn't make a lot of sense with that information to ascribe probabilities to -1 and zero infinity, because we only have the information that's in one or the other and not the chance of being in either one of them. Like, what we would like to see is that the credibility, so that's how much information we have for or against something. So the credibility that theta naught is equal to -1, we have no information that that's not true, so we should give that credibility 1. And we have no information that the credibility, no information that theta is not in zero infinity, so we should also give that credibility 1, and then give everywhere else credibility 0. But we should also have that the credibility of theta naught being in the -1 and or zero infinity should also be 1, because we have no information that suggests that theta naught shouldn't be in there. But clearly that breaks additivity and kind of leads naturally to relaxing additivity to subadditivity. So just to summarize, what we want from a representation of deterministic uncertainty is a faithful representation of the true value of the parameter as something fixed. It should give a full characterization of uncertainty. It should be relatively easy to compute and shouldn't have this additivity requirement that probability theory does. Okay, so relaxing additivity to subadditivity leads naturally to possibility theory. Okay, so we replace probability measures with outer probability measures, which you've probably come across outer measures when you did measure theory, when you use it to define the big measure or whatever, but they're not generally used. But here they make sense because they are essentially a probability measure with the additivity condition relaxed. And for them, we can define possibility functions analogous to PDFs, but this time, instead of an integral like we would with PDF, we have a supremum, which is because of the additivity changing to subadditivity. But it makes sense with our intuition that sorry, I forgot to say this. The possibility, the P bar, we call possibility or credibility interchangeable. So the possibility or credibility of a event A should be at least as big as all of its subsets because of the subadditivity condition. So it makes sense with our intuition to have this as a supremum rather than integral. And if we go back to our example with the -1 and 0 infinity, if I gave you the set -2 to -0.5, which obviously -1 is contained in, then the credibility that it's in -2 to -0.5 is, the question is, do we have any information that suggests it's not in that set? And the answer is no, because we know it's -1 or 0 infinity, and we have no information that suggests it's not -1. So the credibility of -2 to -0.5 should also be 1. Okay. Then we can define uncertain variables as an analog of random variables, but here they're just surjective mappings onto the parameter space, because we have no measurability conditions anymore because we got rid of that. And we have one true value, which reflects what we know about deterministic uncertainty. There is one true value. Okay. And very similarly, we can develop Bayes' rule for uncertain variables and hence perform like Bayesian updates in the same way that we would in the probability case. So if we go back to our list of requirements that we had for describing deterministic uncertainty, we wanted a faithful representation of the true value of the parameter as a fixed quantity, and we've got that here with theta naught is equal to the uncertain variable at omega naught. We wanted a full characterization of uncertainty, which we'll get with the Bayesian updates. We've got relatively easy computation because in the denominator we've got a supremum now, which is generally easier to calculate than an integral. And we've also relaxed the additivity requirement, which was the whole point of possibility theory. Okay. So going back to reinforcement learning, how do we apply this to a problem? Yeah. So the starting point is differentiating between what is due to random and deterministic uncertainty. And I guess with every real world problem, there is some philosophical debate to have about what is actually random and what is deterministic, because you could argue with enough information that anything is deterministic. But I usually would think of it as it's random if you do not have the ability to gain the information that would make it deterministic. So we said that random uncertainty can't be resolved with information, and deterministic uncertainty can be resolved with information. So we consider things random if we don't have the information to resolve the uncertainty. Okay. So essentially, we just need to figure out what we want to model as random and deterministic uncertainty. So in our example with the car, the way braking is affected, so your actions affected, could be random uncertainty because you will never be able to gather enough information about the road surface, the amount of water, any grease that would actually tell you what the true value of how effective your braking will be. Whereas the uncertainty in position caused by GPS could be considered deterministic uncertainty because you are in one fixed place and you can work to resolve this uncertainty with the other sensors you have, so the cameras or whatever would give you an exact location. Okay. So obviously in real world there's a lot of things that are dependent on both random and deterministic uncertainty, and possibility theory can deal with those as well. And in some sense that's the real potential of possibility theory on this problem, because in reality most things are deterministic or random, but there's not really too much time to talk about that. But you can do very similar things and derive a Bayes rule for uncertain variables that are dependent on both random and deterministic uncertainty, and it all works out quite nicely. And it gives you a very different structure to probability theory, which will hopefully lead to some quite different results. Okay. So just to finish up, so what have I actually been doing so far? So I've applied this idea for the parameters to multi-arm bandits. So that's essentially you've got n slot machines and they all have a different expected return, so expected value from playing them, and you want to explore the slot machines and then eventually exploit the best one. So we got some promising empirical results from basic algorithms in the setting that were derived from possibility theory, and also found a new, in my opinion, much more intuitive justification for KLUCB, which is an existing algorithm that solves the multi-arm bandit problem and is one of one of the best algorithms that already exist. Okay, so conclusions. Yeah, possibility theory has the potential to resolve a lot of the downsides of modeling deterministic uncertainty with probability theory, and has already demonstrated benefits within the setting of multi-arm bandits. And there is definitely a lot of potential in applying this to more complicated reinforcement learning environments, which is what I'm trying to do now. So, thank you for listening, and say thank you to my supervisor and funding councils as well.
Okay, yes, thank you very much. I will stop the recording after the first round of applause, so we can still keep these on camera. So if you would join me in thanking Jake for his talk, and if you could unmute yourselves, yeah. Okay, right, so let me ask if there are any questions for Jake. We still have around 5 minutes for questions. Okay, maybe people are shy, so I didn't stop recording, wait. Yeah, just a second. I need to find out how to do this. Okay.